Hey, hello, you're welcome again to lesson 4. And today we'll be treating the design of a double shear joint, or it's still a bolted connection, but this time around we're dealing with the design of a double shear joint. In the previous lesson, I showed to you how to design a single shear joint from a lap joint. That was just a simple lap joint that in its implication will produce a single shear effect on the bolts. But this, as you can see on my screen, is going to have a double shear failure effect on the bolts, and that is exactly what we're going to be designing today. So in this example, we'll be the example says a lap joint. You see that this is a lap joint similar to the earlier example that we did. That was exactly a lap joint is shown, and in this case there are two shear interfaces. I explained to you why we have two shear interfaces, all right, because this exactly would fail in double shear mode. And we have four 20 mm diameter grade 8.8 black bolts. So we have the information about the bolts, grade 8.8. The outer plates are 8 mm thick. The outer plates are 8 mm thick, whilst the inner plate is 12 mm thick. All are S27 steel. So what are we supposed to design for? We are going to design for the end distances, all right. We're going to design for, or check rather, for the bolt spacing, just like we did in the previous example. And we're also going to check for the bolt capacity, and I told you that the capacity is either in shear or bearing. We saw that in the last example. And also we're going to check for the bearing, the plate bearing capacity, just like we did in the previous lesson. And in the next lesson, I'm going to speak about plate tension capacity, because there is also plate tension capacity. And then I'm going to speak about the block shear. There is also the block shear. So these two comes next, while we treat A, B, and C. Now to start with, bolt spacing. Bolt spacing. Just like we saw in the previous example, the code according to clause 6.2.2.1, and as a way of reminder, I would like to show to you from the code of practice BS 5950. So this is what we have now, 6.2.2.1. So let's check what's all about 6.2.1. So it speaks about the edge and end distances, and I've been able to pick out the parameters for us. For the minimum edge distance, it should not be less than the value in table 29, which we have here, 1.25D for rolled machine flame cut, and for shared or hand flame it is 1.4D. And I told you in the last tutorial that we are working with assumption that all edges are either rolled or machine flame cut. All right, so the edge distances in our own case stays within 1.25. So but what we want to deal with is, what we're dealing with is the bolt spacing. So these are the edge distances. So the bolt spacing 6.2.1. all right, so we have, for standard clearance holes or fitted bolts, the spaces between center of bolt should not be less than 2.5 D. So this exactly applies to our design. Okay, so going back here, we have the minimum bolt spacing. Minimum bolt spacing is equals to 2.5 D, and is a small d. All right, the diameter of the bolts we have given is 20, so that is 2.5 multiplied by 20. All right, and that should give 50 mm. You see that now? So the maximum bolt spacing, from that same clause recommends 14T. all right, and that's the 14 multiplied by the thickness of the plate, and we are being told that the thickness of that plate, the outer plate, is 8 mm. Okay, so we have 112 millimeters. All right, so it means that for your bolt spacing, 50 mm should be less than or equals to your spacing, your recommended spacing, and then your spacing should be less than or equals to 112 mm. So any value you pick between the lower limit and the higher limit would be a correct one. So that's how we deal with the bolt spacing. Okay, so in this case, we pick 50, you are still good. If you pick 70, 75, you're still good. 100, you're still good. All right, but it shouldn't be necessarily too large, so 50 mm is fair. All right, so the next one we want to do is to check out for our bolt capacity. So let's not forget the diameter of our bolt is 20 mm. Okay, and just to refresh our memory, the minimum edge distance, I taught this in the last tutorial. Okay, which you can obtain this from clause 6.2.2.5. okay, is 1.25 D, and that should give 1.25 multiplied by, you remember this is a capital D, that is, you must have observed the standard clearance hole diameter, which would be 2 mm. If you need to refresh something, you need to go back to the last tutorial to check how we got about that. So this 22, then the minimum edge distance in this case would be 27.5 millimeters. Okay, what about the maximum edge distance? The maximum edge distance, still from that clause, okay, and that would be 11T epsilon, and I show you what epsilon exactly would be from the last example. So the thickness is 8, and epsilon, seeing that we are using S275 grade, would be equals to 1, and that would be 88. You see that now? So it means that whatever you are using, your recommendation should be such that 27.5 mm is less than or equals to the distance you're recommending for your end or edge as the edge distance, and then it should be less than or equals to 88 millimeters. So in this case, we used 40, as you can see in the question is 40. So 40 would be correct in this case. So sometimes you may need to check whether the edge distances are appropriate or sufficient, then this will be a good one. All right, okay, so back to our question. I just needed to refresh your memory as per the last class. So the next question now would be bolt shear capacity. Bolt shear capacity. Bolt shear capacity. All right, so the bolt shear capacity from our clause 6.3.2.1, I hope you remember that. Okay, it says that a capital P subscript S is equals to small p subscript s multiplied by as. Okay, so for a grade 8.8 bolts, okay, for grade 8.8 bolts, you would see from that table 30 that the shear strength is equals to 375 Newton per millimeter squared. All right, so you can check that from table 30 of 5950 in case you need me to show you. Table 30 5950. So you see what's there now. Shear strength of bolt grade 8.8 bolt is 375 Newton per millimeter squared. Okay, so for this one now we have that to be that. So from table for the tensile area of 20 mm bolts, okay, for the tensile area of 20 mm bolts, I showed you from the steel designer manual that I sent to you. All right, so you need to begin to check that for yourself so that you can confirm the validity of this information. Okay, so the tensile area of a 20 mm bolt from that steel manual, it should be 245 millimeter squared. All right, okay, so putting all these things together, we can have the shear capacity to be 375 multiplied by 245 millimeter square. Okay, and that should give us 91.9 kilonewton. So this is the shear capacity of the bolt. All right, that's great. Now, but you not forget that we are having two shear planes. Recall that there are two shear planes. We're having two shear planes. Now this shows a single shear plane. Okay, so it means that what we're supposed to do to have the maximum shear force, would have 2 multiplied by 91.9 kilonewton, and that should give us 183.8 kilonewton per bolt. All right, so having obtained the maximum shear force of a bolt in two shear planes, all right, we are supposed to now look for the maximum applied force per bolt. What we're trying to say is this: what we obtain here as the maximum shear force per bolt is the shear capacity of a bolt subject to two shear planes. That's the capacity of the bolt itself. All right, now what we need to get now is the maximum applied force as a result of the external force connected to that bolt group. So in this case, the external force or the applied force to this bolt group is 150 kilonewton from the question here. Let me point it out to you. So this is what we're talking about here. 150 kilonewton. Addition of these two also 150 kilonewton. You see that now? So that's exactly the applied force on that bolt group. All right. So we want to now find out the effect, how much of this force goes to each bolt, and we have 4 of these bolts in that group, and that will be 37.5 kilonewton. All right. So this is the amount of load or force rather that goes to each bolt, and this is the capacity of each bolt in double shear. I hope it's clear enough. All right, so we can move further. The next thing we want to calculate now is the bearing capacity of a bolt. Bearing capacity of the bolt. Okay, so the bearing capacity of the bolt from clause 6.3.3.2 of the code, and then we're going to apply table 31 along the line, if you have not forgotten. So we have PBB is equals to DTP PBB. All right, so this would give 20 mm diameter multiplied by the thickness of the plate, and the thickness of the plate in this case is 12 mm. all right, because this is the bearing capacity, then multiplied by the PBB from table 31. all right, our PBB is 1000 Newton per millimeter square. All right, from table 31. You may just reference table 31 for that. Okay, now this is why we picked, I know you have a question, why did we pick 12 and not 10 mm? I mean 8 mm. Why did we pick 12 and not 8 mm? All right, this is the inner plate and this is the outer plate. Now the aggregate thickness of the outer plate, all right, is observed to be greater than the inner plate. All right, so the capacity of this would rather be obtained using this and not this, because this is greater than this. I hope you got that. Great. So if you get that, then we're good. So the capacity of the bolts, the bearing capacity now, would be 240 kilonewton. 240 kilonewton. And you discover that this exactly is greater than the applied force. You see that now? So our bolt group is still safe, both in bearing and then in shear, seeing that they are both greater than the applied force. All right, so we have obtained that too. The last one we're going to do in this lesson is to obtain the plate bearing capacity. Plate bearing capacity. All right, and to do that we want to reference our clause from the code, clause 6.3.3.3, and then table 32. So the bearing capacity of a plate from our code of practice is obtained from the relation KBS DTP PBS. All right, so from this we can actually substitute from our code of practice. KBS is taken to be as 1.0. if you do not forget, I showed to you in the last tutorial. So we have it to be 1.0 multiplied by 20, which is the diameter of bolt diameter, then the thickness of plate, that's 12. I showed you why it's 12, and then PBS 460, and this will be 110.4 kilonewton. Now you see that the plate bearing capacity itself also is greater than 37.5 kilonewton. So what can we say based on our calculations in this lesson? That we can conclude that the bolt spacing is adequate. All right, the bolt shear capacity is adequate. The plate bearing capacity also is adequate. So this design is actually perfect for the loading it is subjected to. So in the next lesson, I'll be showing to you how to design for block shear and then plate tension capacity. If you do have any question around this that I've shown to you in this lesson, please do well to reach out to me and let me know so that I can help you out. See you in the next lesson. Bye.